We want to finish the law of cosines. Remember the law of cosines? It said this: in any triangle, marked in our usual way, we'll call one of the angles alpha, one of the angles beta, and one of the angles gamma. It doesn't say which one is which since it's not a right triangle. Opposite alpha, we put A. Opposite beta, we put B. Opposite gamma, we put C. It turns out that C squared equals A squared plus B squared minus 2AB cosine gamma. Now, I wanted to point out, I like another presentation of this. In some books, instead of using alpha, beta, and gamma for the angles, what they'll do is call this point capital A, and this point capital B, and this point capital C, and then they'll call it angle A, angle B, and angle C at those 3 points for the triangle. And they'll write it like this: C squared equals A squared plus B squared minus 2AB cosine C. And this law is as easy as your ABCs, right? A squared plus B squared minus 2AB cosine C, ABC, just in that order. Makes it very easy to remember. What's more, I'm going to put this back as gamma to match the book here. But I just thought if you forget, C, right? Helps you remember. That helps me anyway. The other thing is it's an extension, a generalization of the Pythagorean theorem, right? This part, C squared equals A squared plus B squared, is the Pythagorean theorem. That applies only to right triangles. And here's the proof. Since you can see the proof in the book, we won't do it here too long. Since the law of cosines proves that C squared is not A squared plus B squared in general, but is A squared plus B squared minus 2AB cosine gamma, this only works if this part is 0. Well, when is this 0? When this angle is 90 degrees, right angle, then cosine is 0, and you get the Pythagorean theorem as a special case of the law of cosines. So this works for all triangles, including right triangles. In this case, this term falls out, and you get the Pythagorean theorem. So don't apply the Pythagorean theorem to these oblique triangles we're doing in this section. In this section, we won't have any right triangles, and the Pythagorean theorem won't work. You have to write the law of cosines, right? So that's what we had. And then we said by relabeling all these sides, we could equivalently get A squared, if you like ABC in order, A squared equals B squared plus B squared, C squared, minus 2BC cosine alpha, the angle opposite this side over here, always. So C on the left with gamma on the right, A on the left with alpha on the right, or you can reorient them again and write B squared equals A squared plus C squared minus 2AC cosine beta. And you'll see it put in all 3 of those forms. There's 3 law of cosines, just like there's 3 equations to the law of sines. But really, they're all equivalent to relabeling. So I'll just call this one 1. This is the one that's easiest to remember because it looks like the Pythagorean theorem almost. And we want to use this in what cases? Remember, given side, 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 or side, angle, side information in a triangle. Because what happens is if you're given those, the law of cosines will give you all but one known in the equation, and you can solve for the last unknown, right? So that's why it's good for these. You can solve it quickly. It applies to any triangle, but in particular, if you're given this, you can use it to solve for one of the other things quickly. There'll only be one unknown in the question, in the equation. Just like with the law of sines, if you were given angle, angle, side, angle, or side, side, angle data, then everything with the law of sines, except for one quantity, was known, and you can solve for the one unknown. So law of sines quickly solves oblique triangles in those 3 cases, all the cases that cosines doesn't. And the law of cosines applies to these 2. That's the easy way to remember it. Law of cosines applies to these 2 cases to solve it quickly, even though it applies to all triangles. Law of sines applies to all the other cases quickly, right? And you can now solve with this any oblique triangle. Isn't that great? So you're triangle experts at this point. So let's try an example. And we did a quick example at the end last time, but I want to make sure I do this one. I used to work for the FAA for years. And so this kind of problems are close to my heart. Here's one of mine, your homework. In section 7.8 is where this, I'm sorry, 8.2 is where this is. And it says, let's see, this is number 8. Pilot flies straight for an hour and 30 minutes. One hour, 30 minutes. On there, I guess just barely, yeah, okay. And then turns 10 degrees. And flies for 2 hours. Turns right 10 degrees, let's say. The trip is all at 680 miles per hour. mph mile per hour. How far is the pilot from her initial position? It says, how far is the pilot from home, let's say? For a quick expression. On these applied problems, what did we say before really helps? In trigonometry especially. Draw a picture, right? I'm going to draw a picture. And often a picture tells you what you need to know to finish the problem. This one needs a picture for that reason. There's the sketch. The pilot, it doesn't say what direction, let's just pick it north here, flies a certain distance. Well, then it tells us that distance. And then the pilot turns right. So let's say, I think that's what the instructions say actually is right. And at a 10-degree angle, and flies for another distance. And here's the finishing position. Here's the starting position maybe here. And what we want to know then is how far apart are these two dots. In your sketch, what you should do is draw all the things you know and what you want to find out. So here's one thing I know, 10 degrees. What I want to know is this thing. So I can call this D for distance. That's a good letter. Because I'm going to use the law of cosines and try and find this side, I'll call this side C. Right? One of the A, B, or C. Just so I can put it in directly in the law of cosines. Now, what are the other two sides? I'm given some things here, right? What is the length here of side A? Say, call this A, doesn't matter which one. There's always a law of cosines that applies, right? Well, A can be written as flying for 1 hour and 30 minutes is 1.5 hours at 680 miles per hour. So it's 680, and I'm going to write the other notation. Miles divided by hours is also miles per hour. It's longer to write, but it's more suggestive for us when we're using units here. All right. Because now we notice that the hours cancel, and we got 1.5 times 680 is 1,020, right? 1,040, all right? Okay. No, 1,020 miles. All right. So that's how far the pilot flies on the one leg. Then on the other leg, she's supposed to fly 2 hours. So B would be 2 hours times 680 miles per hour. And so now we've got 1,360 miles, right? The hours canceling again, you get miles. And 2 times 680 gets 1,360 miles. Now we know, we've written down everything we know, right? This is 1,020 miles. This is 1,360 miles. This is 10 degrees. And we've written down what we're trying to find, C. So you apply the sketch to figure this out. And we don't know yet we're going to use the law of cosines, except because it's in this section, right? But what do we have? Remember, to solve a oblique triangle, we need three pieces of information other than angle, 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 which isn't a congruence theorem, right? Neither is side, side angle, but we can still do something with that. All right, so let's see, we know a side and a side. We know this angle outside. You know what? Because this angle and this one are supplementary, add up to a straight angle, 180 degrees. We know this one must be 180 less than 10 degrees. It must be 170 degrees. So there's where the picture comes in. Now I can see I have a side, an angle, and a side that I can figure from the sketch. And oh, side, angle, side. Remember, that's one of the two cases. I use the law of cosines. The law of sines applies, but when you write the law of sines, you won't get an equation with only one unknown, and it'll be hard, right? So you want to do the easy one, use law of cosines. What does the law of cosines say? I want to pick the one of the three of these that solves my problem, right? I want to find C, so I need C in there. But the key here is that I'm given gamma and A and B. So I look at the first equation. If I'm given A, B, and gamma, I know everything but C. So I'm going to use by the first equation of those. One, the law of cosines. C squared equals A squared, that's 1020 squared, plus B squared, that's 1360 squared, minus twice A, B, cosine of the angle between them, gamma. There it is. Now I can get it. I'm trying to find C, the distance the pilot is from the starting point. All I have to do to get C squared is this number, then I'll just square root it. Right. So what is that? This is 1020 squared plus 1360 squared is 2 times 1020. 1360 times cosine. Make sure you're in degrees mode here. You get the wrong answer, right? Cosine 170. And I get this huge number, right? 5622250.63. It's huge because it's a square of the distance. So we're not really going this far. This is the square. So C is the square root of all this. So this goes in here. And now if I'm on my calculator, how I can get this rapidly without risking fat fingering it like I always do in here when I push too many keys to put in all these digits. Right? It's not a digit. I'll probably make a mistake. So instead of typing all those in again, I'll say second x squared, because up above x squared is the square root key, right? It'll automatically insert a left parenthesis to take the square root of. Then I'll push second ands, which is up above the little negative key, and enter. And what this will do, it will put on the screen square root from these two keys, and then it will put in the last answer. I think it just puts A and S. Let's see. Second square root, second ands. Yeah, puts square parenthesis A and S on this TI-84. And then you can close the parenthesis just to be careful, or you can leave it off. This one will automatically close. Let's leave it off and say, it doesn't put the number up yet, but when I push enter, it gives me the number. I get 2,371.12. Let's just say to the nearest mile is 2,371 miles. Then you look at that and you always do the sanity check. Does that look about right? Well, 1,020 and 1360 would be 2380, a little more than this. So since it's such a slight angle term, that's probably right, right? So that looks reasonable. I'll keep it. But if you got 2,000 miles, you made a mistake somewhere. How about that? Side angle side. Use the law of cosines, the version of it, one of the three, that has all but one number known. Easy. But here's one of my favorite law of cosines problems too. You've seen this wonderful 3, 4, 5 right triangle, right? We solved for the angles in it. We always wanted to know what they were. We could do it using inverse trig. What if instead I gave you the oblique triangle? Out in my backyard, I'm going to make a garden, right? And I don't have sticks that are good lengths. One to make a right triangle. Maybe I have a stick that's length 3 and one that's length 4 and one that's length 6. So I'm not going to have a right triangle garden. And I'm wondering, what are the angles between the boards here? Maybe I want to cut these so they mesh nicely, right? So I'm going to angle them. I need to know what angle to cut my boards at. Nail them together. How am I going to decide what angles there are? We'll say for this one, solve the triangle. It's not a right triangle, so you can't use your old methods. We have to use the law of sine. Well, you can if you draw perpendiculars, for instance. But without long work, we need the law of sines or cosines. Solve this triangle. Again, in all these problems, you're given 3 pieces of information. In this case, we notice it's side, side, side. Since it's side, 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 that's one of the 2 cases for the law of cosines. All right, so I'll use the law of cosines again. And since it's all 3 sides, it doesn't matter which of the 3 versions I use, right? They're all the same. So I'll just use the one I'm most familiar with, the Pythagorean theorem, c squared equals a squared plus b squared, minus twice the ABCs, right? Twice AB cosine C or gamma. We'll use that one. And let's see, I'm going to do a thing here that I'll recommend for your homework. What's wise when you're doing this with side, side, side is to let C be the largest side. So I'm going to choose C to be this one and then choose A and B. It doesn't matter. Just for convenience, I'll choose A to be the short side and B to be the middle side and C to be the long side. That's easy to remember, right? Bigger and bigger and bigger. And then I won't make mistakes maybe. So A squared is 3 squared. B squared is 4 squared minus 2 times 3 times 4 times cosine gamma. Gamma I don't know this time, but I know C. 6 squared equals 3 squared plus 4 squared minus 2, 3, 4. Cosine gamma is this nice triangle. And here's what's nice about the law of cosines for side, side, side. I know all but one quantity, and that's the angle, and I can solve for it, right? So how do I do this? I can compute these numbers now, but sometimes I like to just write this down and then compute it later. Suppose I subtract the 3 squared and 4 squared from both sides and write equivalently 6 squared minus 3 squared minus 4 squared equals negative 2 times 3 times 4 times cosine gamma. How can that be? All right, this is 36 minus 9 minus 16. It's positive. How can it be equal to a negative number? I got a solution for that. How can this be equal to a negative? Yeah, the cosine is negative, right? What happens is, and when is the cosine negative? Anybody remember that? That's a tricky question. When is the cosine of a triangle angle negative? And when is the cosine of a triangle negative positive? A triangle angle is between 0 and 180 degrees. If it's in the first quadrant, it's positive. So an acute angle, this will be positive. I know because this has to be negative to match the positive on the left side. This is going to be an obtuse angle. An angle bigger than 90 degrees will have cosine negative. So it's okay to have the negative here. It just means cosine is negative because gamma is an oblique angle, obtuse angle. So I'll go ahead and finish this up. There's nothing wrong with it. 6 squared minus 3 squared minus 4 squared. And I'll divide by this, negative 24. That's what this is. And that's the cosine of gamma. Well, cosine gamma is that number. What must gamma be? Be the arc cosine, right? So equivalently, gamma is the inverse cosine. The angle that has that cosine that's between 0 and 180 degrees is the arc cosine. Arc cosine of 6 squared minus 3 squared minus 4 squared all over negative 24. Right? So I run out of my calculator. Let's see. Cosine. And comment on your calculator here. If you have an old clunky calculator like I have in my hand, and you put these instructions in, you're liable to get, without parentheses, you're liable to get the wrong answer because remember it follows order of operations. And if it doesn't show you this long bar, then what it's liable to show on the screen is something like this, divided by minus 24. And this is wrong if you put this in, because what it'll do is the division first, 4 squared divided by negative 24, then it will do this subtraction and then subtract this number. It will subtract all this stuff doing the division before the subtractions, right? So make sure that if your calculator is an old clunky one, not showing the long bar, you need to put parentheses around these, right? Just on the calculator, not on the board. But let's do that. Then I'll put parentheses around those and say, what is the arc cosine of parenthesis 36 minus 9 minus 16? I know the squares, right? Close parenthesis divided by negative 24, close parenthesis. And I get approximately, rounded off, 117 degrees. There we go. I got one of the three angles fairly quickly by the law of cosines. So side, law of cosines gets you one angle. That's step one, right? To solve a triangle, I'm given three pieces of information. I have to find three. So I found one that gamma is 117. Now, what's the second step? Yeah.
Law of sines?
Yeah, law of sines. That's a good guess. You can use the law of cosines if you want. I won't mark you off on the test. But you notice law of cosines is just a little longer than the law of sines. So you can actually use either one you want, either the law of sines or law of cosines. And almost every book I see uses the law of sines at this point. That's because it's shorter. All right. So the law of sines now says that the sine of gamma, the angle I found, I need to use here. Otherwise, I don't have enough information. I just have side, right? But now that I have this angle, I can use the law of sines. Sine of 117 is to C, its opposite side, 6. As let's do alpha here. Sine of alpha is to A, which was 3. All right. So there's one of the three equations for law of sines. One of them that has only one unknown in it, right? So now I can solve for that unknown. I'll multiply by 3, and this is equivalently 1/2 sine 117 degrees equals sine alpha. Well, it follows by the inverse sign, doesn't it, that alpha, taking the inverse sign of both sides, must be inverse sine of 1/2 of the sine of 117 degrees. There it is. Oh, wait a minute. There's another possibility, right? What's the other possibility? For law of sines, the ambiguous case? Yeah, it might be 180 minus. So it might be alpha is 180 less this same inverse sine. Here's where being prudent is going to pay off. I can actually throw this case out. It's not going to happen. In general, you have to check both cases to see whether, whether maybe it's 180 minus, because both those angles will have the same sign. But here's what we did on the first step. I said, I'm going to think ahead and pick in the side case and pick C to be the longest side. Because now what I found, if this is the longest side, the opposite angle is the largest angle, right? So I found the largest angle. But I know something about triangles. In a triangle, there can never be more than one angle that's obtuse, right? The angles have to add up to 180 degrees. If I take two angles bigger than 90, they already add up to more than 180. So I can only have one angle at most that's obtuse, bigger than 90 degrees, or even equal to 90 degrees. If this is the largest angle, then the other two angles cannot be obtuse, right? They can have at most one obtuse angle. So we know that this one is not bigger than or equal to 90 degrees because we found the largest angle. And But the 180 minus case is always an obtuse angle, or 90 degrees if you do it just right. But it can't be the 180 minus case. That would be an angle that's at least as big as 90 degrees. So here's the nice thing. When you do side, 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 find the largest angle first. Then you don't have to consider cases. You just take the arc sine, and that's it. It has to be the arc sine. Oh, wait a minute. What about this? Maybe there's an ambiguous case with the law of cosines. Do I need to take a 180 minus this? The answer is no. The law of cosines has no ambiguity. And it doesn't matter which side you pick, which angle you pick. There's never any ambiguity. For this reason, the inverse cosine always gives you the unique angle between 180 degrees, which is what triangle angles are, that has the cosine. There's only one angle that has this cosine that's between 0 and 180 degrees. And so inverse cosine is it. So there's no ambiguity in the law of cosines. You don't have to consider two cases. And then if you got the largest angle from that one, you know the other angles, you don't have any ambiguity using the law of sines. So there it is. It's just the inverse sine. Alpha must be equal to, and let's run this on the calculator then. Inverse sine, making sure it's in degrees mode, right? 0.5 times sine 117. And I get 26.45 degrees. Let's say it's approximately 26 degrees. Okay. So there's the second angle. But I have one more thing to find, right? Given three pieces of information, three measures, I have three more measures to find. What's the last measure? I can use the law of cosine, great difficulty. I use the law of sines with a little less difficulty, or I can subtract, right? I have two angles. I can always find the last one immediately. Beta must be 180 minus the two angles. 180 minus 26 minus 117. Let's see, that's 143, right? So this is 37 degrees. There's the last angle. Is that right? Uh, 130, 143. Yeah, okay, good. So there it is. We solved the triangle, starting with the law of cosine, switching to the law of sines, and then subtracting. That's how you do all of the side, side, side examples, except this one. I'm going to change this a little. Is this good? Any questions on this one? Now I'm going to change it. Oh, instead of a 3, 4, 3, 4, and 7, 6 triangle, what I have sitting out in my garage to make a garden is 3, 4, and 8 foot things. Now suppose I want to solve this triangle. What do I get? This is the easiest problem in the whole section.
It's larger than the two others.
There you go. Yeah, 8 is bigger than these. The shortest distance between 2 points is always a line. 3 plus 4 can't be less than 8. This is an impossible triangle. There's no solution because there's no such triangle. That's one of the reasons you do that check at the end. So you don't have to do anything. Just say there's no solution. What happens is the law of cosine says in any triangle, but if you apply it to this one, you'll get like negative numbers and say, well, I'm not getting negative numbers. I did it just right. It's because there's no such triangle. So it only applies if it's really a triangle, and this one's not. All right. So that's the last and easiest example that we'll give on that. Okay. Try all those problems out of 8.2, except the last one. We want to do the area problems next time. 8.2, 1 through 9. And here's the good news. That's the end of what we formally call trigonometry. With that concept. The rest of what we're going to do is going to be applications. Very important also, but if you get through with this, you'll be able to figure this stuff out and take calculus or whatever else. Okay. I'll try all those homework problems, see how they go, bring questions as you have them. And the next section is one we skipped. We're gonna go back and, I forgot to say this one. Actually, there is one more topic. Sum to product and product to sum formulas. Is that with this is the end. These are just what they're called. And these are worth doing the derivations because these are so easy to forget. And actually, you notice I put this section off. It's because this is some of the least important material in the chapter. They have all these other identities. This is at the very end because it's used the least, I think, and it's derived from some of the others also. So here's the first one. Suppose we look back at these sum and difference identities. We have cosine. Cosine of alpha plus beta. What is that? That's equal to cosine alpha, cosine beta, minus sine alpha, sine beta. I remember the sum identity. Cosine of the sum plus goes with minus. Now I can also write the difference identity, right? Cosine of alpha minus beta is equal to cosine, cosine plus sine, sine. There it is. And if I take these two equations and I add them, what happens? On the left, I get cosine alpha plus beta plus cosine alpha minus beta is equal to these two adding to double 2 cosine cosine. But these two cancel. And so I get that equation. Now suppose I divide by 2 and switch sides and get an equivalent equation. We'll say this is equivalent to, divide that side by 2 and put it over here, it gives cosine alpha, cosine beta. Then divide this side by 2 and put it over the right side, and I get 1/2 cosine alpha plus beta plus cosine alpha minus beta. There it is, our first product to sum formula. Takes a product of cosine functions and rewrites it as a sum times 1/2 of cosine functions. Product to sum identity. I'm going to put an equation number here, 1, because I want to refer to it. But I'm going to say you don't have to memorize these, no star on this one. These things are not used that much. What you need to do is know they're there, that you can convert a product to a sum, but you don't need to have them memorized. They're not used that much. All you do is Google product to sum identity, you can look it up on the web anytime, right? This to me is amazing, if you really think about it, right? Suppose I take 2 waves, 2 cosines, right? They wiggle up and down, and I multiply them together. What kind of crazy wave could that be if I multiply 2 waves together? Turns out to be just the same as summing 2 waves. Where else do you ever see that a product is equal to a multiple of a sum, right? Half of a sum. This is kind of a startling consequence, and it has some interesting implications when you do vibration analysis and circuit analysis and those kinds of things in your applied courses. So there's the first product of sum identity. Similarly, we can now subtract those two. Well, I subtract the let's take the second one minus the first. Then I'll take cosine alpha minus beta less cosine alpha plus beta on the left-hand side, right? This one minus this one is equal to this one minus this one. Now the cosines cancel, and I get this one minus this one is 2 of these. 2 sine alpha sine beta. There it is. And if I, again, switch sides and divide by 2, I get equivalently, 1/2 of this on the left is sine alpha sine beta equals on the right 1/2 of this, 1/2 cosine alpha minus beta minus cosine alpha plus beta. There's our second product of sum identity. Product of sine functions is equal to 1/2 this difference of cosine functions. You can think of this as a product of sum because it's minus cosine of minus this angle technically. But I'll still call it a product of sum identity. So there's a second product of sum. Identity. And we want one more because what if we have here we have cosine times cosine converts, sine times sine converts. What if we have a sine times a cosine, right? So we'll go and look at that and say, also, we have some sum and difference identities for the sine function. Sine alpha plus beta, we recall, is sine cosine plus cosine sine, with the sum identity for sine plus goes with plus. And similar to the difference identity, minus goes with minus. So sine of alpha minus beta is sine cosine minus cosine sine. And we do the same as before. Suppose I add these, right? Then I get this plus this on the left, sine alpha plus beta plus sine alpha minus beta is on the right. These two reinforce each other. You get two of them, 2 sine alpha cosine beta, but these cancel, right? And you just get this equation. Again, if you switch sides and divide by 2, you get equivalently. On the left, this thing over 2 is just sine alpha cosine beta. On the right, this one over 2 is 1/2 sine alpha plus beta plus sine alpha minus beta. There's the final product of sum formula. If I have a sine times a cosine, I can do this. We can call this equation 3. Well, that's amazing. A product is equal to a sum. But if you really think about it, if a product is equal to sum, then doesn't it say that the sum is equal to the product? It certainly does. It's just a matter of writing it out carefully. So I'm going to go back now and get some more equations, actually 4 more out of this. We may not prove all of them. Let's just do one of them, I think. Spend too much time on proofs, you won't be awake for the last part, right? So let's go from equation 1 here. If I'm substituting, letting theta equal alpha plus beta, the thing I see in this cosine, and let gamma be alpha minus beta, what I see in the other cosine. So that, right, that gives theta and gamma in terms of alpha and beta. Now, what is alpha and beta in terms of theta and gamma? If you add these two and divide by 2, you get 2 alpha. By adding, you get theta plus gamma equals this plus this. The betas cancel, you get 2 alpha. Which then you divide by 2 and you get alpha is theta plus gamma over 2. That's, if you make these substitutions, theta is alpha plus beta, gamma is alpha minus beta, then this is what alpha comes out to be. And then if you subtract these two, this one minus this one, theta minus gamma is going to be this one minus this one. The alphas cancel now, and the betas reinforce. You get 2 beta. Right? And then divide that by 2 and switch sides. It tells you the beta is theta minus gamma over 2. Right? So you make that substitution. Theta is alpha plus beta, gamma is alpha minus beta. And this is what alpha and beta are in terms of theta and gamma in that case. 1 becomes, here's 1, we just put those things in. Alpha we replace with, where'd it go? Theta plus gamma over 2. 1 becomes cosine theta plus gamma over 2 times cosine beta is cosine beta is theta minus gamma over 2 equals, right, we're doing this equation with alpha and beta replaced. 1/2, and now it's easier because you have cosine of alpha plus beta, but alpha plus beta is beta, that was the original substitution. And plus cosine alpha minus beta is cosine alpha minus beta is just gamma, so you have this equation, right? So just substituting into equation 1 with theta equals alpha plus beta and gamma equals alpha minus beta gives us that. Now multiply by 2 and switch sides. Multiply by 2, switch sides. You get, what do we get? I'm gonna get rid of the. This 1 times 2 over here gives us cosine theta plus cosine gamma. And then this 1 times 2 on the other side gives twice cosine theta plus gamma over 2 cosine theta minus gamma over 2. There it is, our second sum to product identity. Or first, I'm sorry, sum to product identity. Any sum of cosines is equal to twice a product of cosines. How about that? So let's call that equation 4. Now I want to say there's some more. You derive them exactly the same way. Each of the sum to product to sum identities can be reversed to get a sum to product identity. All you got to do is go to your favorite web browser and say sum to product identity. Let's move the camera over here so people online can see. Oops, I got the camera thing off also. There it comes. There it is. So I just Google sum to product identity, and all these things come up. You just click on your favorite one that looks easy to read. Maybe I'll just go over and click on this one. Now there it is. This is on SOS Math, which is a popular website for math. This is a nice reference. If you ever can't read your textbook, SOS Math and some of these others, Math is Fun, Purple Math, all those are really great websites for getting additional information if anything in your book isn't easy to read. So instead of alpha and beta, they used A and B, but or actually theta and gamma for this. Oh, this is the product of sum. So in product of sum formulas, here's the this was equation 1 that we derived, right? So here's equation 1, just A and B instead of alpha and beta gives you this one. And they actually list 4 of them because I did sine times cosine. You can also do a cosine times sine, but it's essentially the same thing. So you only need 3 of these. There's the product sum identities. And now hopefully the sum to product identities are below them. There you go. There's the product of sum identities, again, written in terms of A and B instead of our theta and gamma. But cosine plus cosine is 2 cosine of the average angle times the cosine of the difference of the angles over 2. That's the first one, but there's 3 more. Here's the second one that you can get by reversing one of the other identities. And here's the third one you get by reversing another identity. And the fourth one they put up there reverses nicely, and you can put this one. So we'll put 4 different sum to product identities, difference of sum of cosines, difference of cosines, sum of sines, and difference of sines. And we'll say there's 4 of these that can be occasionally useful. Again, these are only used once in a while. Let's bring this back now. And say similarly, the other product of sums formulas guess I gotta go read this. Give sine, let's see which one they put up next. They put cosine minus cosine. Give cosine theta minus cosine gamma is minus 2 sine of the sum times sine of the difference over 2. Sine theta plus gamma over 2 sine of theta minus gamma over 2. The third one, if you take the sum of two sines, so this could be 5, and this will be 6, 7 here. Sine of theta minus sine of gamma looks like 2 sine cosine, 2 sine theta plus gamma over 2 cosine theta minus gamma over 2. And the difference of two sines, sine theta minus sine gamma. So whenever you see a sum or difference of sines and cosines, realize that you can rewrite it as a product. And again, that's kind of fascinating, I think, and we're going to show why in just a second. This is twice the cosine of theta plus gamma over 2 times the cosine of theta minus gamma. Sine, sorry. All right. So there are all these, and again, don't memorize these, just be aware that they're there to convert. It's not bad to memorize one of these. This is not a bad one here, number 4 to memorize. That seems to be the most popular in textbooks. Here's why these things are so interesting, is this kind of result that you get out of them. Suppose 2 tuning forks are struck simultaneously at the same time with the same amplitude. Have the same phase, so we'll say with A the same. And so that they're at their maximum amplitude at time 0, so that their net effect, their effect together, is this. If you strike a tuning fork, it has a particularly nice property. Ever seen an oscilloscope where it does a vibration analysis of sounds? You play a sound into it, and it's got this circular, well, not necessarily circular, some of them have circular thing, and it will show you a wave like that. And this might be somebody's voice trying to sing, so it might be. And you can hear a particular note that they're singing because these bumps might have a certain frequency. Think of a sine function going across here. And the vibration, the average vibration frequency tells you what note they're singing. But it's all jumbled in between, and that's what makes a particular voice appealing, is you like this jumble better than somebody else's jumble, but the note is the same, right? The average frequency that's coming through here. But it's really hard to analyze. You have to look at that real careful sometime. And a tuning fork, not so. A tuning fork looks like this. You use it for your musical instruments. If you're a musician, maybe you can tell me more than I know. But it'll be a metal rod like this where you hold on to the handle, and then these 2 tines up here can vibrate. And so you strike this thing, you take the handle and strike it on some hard object, a table or something, and it makes these 2 tines wiggle back and forth very naturally. Steel, if you know, can make this vibrate at a nice sinusoidal thing. And this is how the tines wiggle back and forth. and then they push the air back and forth. And so you get this pressure variation in the air that goes out from where this thing is, right? You get waves going out of high pressure, low pressure, high pressure, low pressure, and they come over to your ear and it goes real fast. But your ear is a super effective instrument. It can pick up these vibrations, and you hear a sound that's based on sinusoidal, and there's no trouble telling the note here because it's nearly a pure sine wave from a tuning fork, right? So you look at that in the oscilloscope, it looks like this, hopefully, if it's a good tuning fork. And so when you strike a tuning fork, the pressure variation in the air from the ambient pressure is A amplitude cosine omega 1t, where this is A cosine, let's do this one, A cosine bt, where B is the angular frequency, right? And in general, you can make a cosine wave A cosine bt minus C plus T. But this is supposed to be the pressure variation, so we'll take D equals 0, right? The natural pressure is 0, or the null variation is 0. And so we'll say this is the pressure variation that makes D equals 0. And also, suppose we start at its maximum amplitude so that C is 0. Now it's real easy. So this is starting at maximum amplitude, the variation from the ambient pressure. And now that's one tuning fork. So I can call it A cosine B1t. And this one has the same amplitude, so it's also A. We'll call it A cosine B2t. And so these are arbitrary cosine waves that are variations from 0 and in phase like this, so that their phase shift is 0. And now I'm going to do something here just for your science classes' sake. In science classes, they do tend to use this letter A and makes you think of amplitude because its absolute value is the amplitude, right? But I'm going to put omega 1 and omega 2 because this angular frequency B, we call it angular frequency because it's the radians per second at which this thing is going. They like to use omega typically, little omega here, not like on the Greek houses, this one, right? So suppose they have two different frequencies. One plays an A note at angular frequency omega 1. The other one plays a C note at angular frequency omega 2. You get these tuning forks, you strike them, and then you can tune your guitar or whatever you're trying to do with them. And so they're different notes maybe because they're two different tuning forks. Pitch two different notes. What happens when you strike them at the same time with the same loudness? And we'll put them in phase just for convenience here. This is the net pressure variation, right? This one makes a constant tune, a constant note, I should say, like that. This one makes a constant note, maybe a little different frequency, right? What happens is the higher the frequency, the faster it oscillates up and down. This angular frequency is the radians per second, right? So if it's a high number, it's high radians per second. And this one, if it's lower, is slower. So you've got two different ones that are a little different. If these omega 1 and omega 2 are pretty close, this has a pretty interesting effect. You apply equation 4, right? This is a sum. I can rewrite it as a product. First one I'll do is I'll pull the A out of there. A cosine omega 1t plus cosine omega 2t. And then I'll apply 4. I'll say then by 4, I'm going to get A times 2 cosine of the average frequency. So we call this the average of the two angles. Right, because it's sum of them divided by 2, just like average of 2 scores. And then we have this one, the difference over 2. So what we'll get here is now 2 times cosine, and the A is still here. So it's 2 cosine, the sum of these two angles, omega 1t plus omega 2t over 2, times the cosine of their difference over 2, omega 1t minus omega 2t over 2. There it is. So striking these things at the same time as it sums their pressure variations, it also is equal to the product of these cosine functions. Well, now I can do something nice on here and say this is actually equal to, let me put it up over here, so I don't block you. This is equal to 2a times cosine omega 1 plus omega 2 over 2t cosine omega 1 minus omega 2 over 2t. Right? You can factor the t out of those. This is significant because what does it say that the sum of these two cosine waves do when I add them? And they're pure notes, they're pure cosines, right? What I get is this. I have a product of cosines where this we call the average angular frequency because it's their average, right? Right? Because it's a cosine of a number times t, the number that multiplies t is the angular frequency. And this one has another name. If you take twice this number, omega 1 minus omega 2, is called the beat frequency. Average one is the sum over 2. And the beat frequency is just their difference then. Oh, I erased the equation I need now. Oh, well. I've got to do Murphy's Law in here somewhere, right? All right, so what you get then, amazingly, when you add, you're adding a cosine wave like this, plus a cosine wave at a different frequency, maybe like that, but not too different. If these are close, but the same amplitude, so they're the same height up and down from the x-axis, what do I get? Look at this, forget this one for a second and look at this one. If I plot y equals 2a cosine omega 1 minus omega 2 over 2t. Look, it's a number times cosine of a number times t. It's a single cosine function, right? That when t equals 0 starts at the origin up here with at 2a. So when t equals 0, you get 2 cosine 0 is 2a. And then it goes like this. It's just a pure cosine, right? A number times cosine, a cosine bt is essentially what it is, right? And so it looks like that. Now that's without this. That's just 2a cosine this part. Now what happens when you multiply it by this cosine function here that wiggles up and down faster between plus and minus 1? Right? You're multiplying this way by something that goes real fast between plus and minus 1. Well, what we can do is draw down to minus 2a here, where this bottoms out, and draw minus this wave also. It's going to come up through the nodes here like that. So this one is y equals minus 2a cosine omega 1 minus omega 2 over 2t. And multiplying by something that goes real fast between plus and minus 1 makes it go like this. And so this is what you'll see on your oscilloscope, where the actual pressure variations in the room. When you strike two of these things that are making pure notes, you don't get a nice single cosine wave. You get this something that wiggles up and down between these two things. And what happens is each one of these things here is called a beat. The sound goes on and off, amazingly. They intermittently support each other and make they're each at amplitude A, right? And make an amplitude that's twice as big and intermittently destructively interact and cancel each other and get 0. And so the sound goes on and off, on and off, on and off. And what's the frequency that you hear? Well, it's this frequency here, when it's wiggling up and down real fast, is the average of the two. So you hear this frequency, and it goes on, and you can sometimes you hear kind of a click, 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 depending on what it is. But you get a sound that goes off and on and off, not with either frequency of these two, the A and the C note. You hear a frequency that's halfway between and goes on and off. They call that the phenomenon of beats. So there's a simple physics example of what you can get out of this. Now, I'm gonna try and show something on the screen, but I don't know how well it's gonna work. If we were just doing the classroom, we could do a nice presentation of this, but unfortunately, what I found is that people online can't hear. So what I have to do is play it out of another source that's not as bright. All right, now let's get rid of this. This is supposed to go off. Oh, it did, okay. So. Here we go. We'll see if you can hear it online. It's gonna be kind of faint here. This is a tuning fork with this handle in the box. Can you hear that sort of? It makes a single note in your guitar. This is an identical tuning fork. He's going to illustrate something different than we talked about first. If you strike this fork, and this one has the same frequency, box amplifies the sound. The handle's down in the box. Then by putting up here the pressure variations in the air go through and strike this one, now you can hear it coming out of this one. So it translates the energy and of the pressure variations into the other tuning fork if it's the same frequency. Now he's going to change the frequency on this one and try this again. Now they're two different frequencies. This one he struck is still playing, but the one that's tuned to a different frequency will not pick it up because it won't pick up what we call standing waves, and because it's the wrong frequency. This is how your radio works. It only gets one station at a time because it's tuned to a particular frequency. Radio waves are like that. Now he's going to strike both of them at different frequencies. Is that going on and off? That's the phenomenon of beats. So you hear a frequency that's halfway between the two tuning forks going on and off. And now you have seen the phenomenon of beats. I hope you can hear that online. I know it was pretty faint in here. I couldn't get my speaker to work, unfortunately. So I just had to play it out of the computer, and it's not very loud. And I don't even know if you can hear it. So if you couldn't hear it, try that. Here's how you can get it online. You want to hear it at home and you didn't get it there. I could write the web address up there. It'd probably be, I'll probably get one letter wrong. You won't be able to find it. But we'll say on Google, for instance, that's where I got that one. You can probably use a different web browser too. Just put MIT, that's who made the video originally, phenomenon of beats. And you'll see that video picture come up near the top with the two boxes in it. And then click on it and you can hear it for yourself as many times as you want. We have some boxes just like those here, but I thought they'd probably do a better job than I do. And I know it works every time because it's a video. So that's the thing. All right, so that's the end of all the stuff. We want to do one example is all. So let's try an example. And again, this is a throwback to section 7.4, all the stuff on. So let's do 7.4, numbers 1 through 3 for homework. In addition to the ones I assigned you in the law of cosines now. Will be problems like this, and these are very easy. There's only 3 problems in the whole problem set, right? So well, here's one example. This is 2A on out of your homework. Rewrite as a sum. Of sine waves. Suppose I gave you a sine wave, I mean either a sine or a cosine function. Cosine of 6t plus cosine of 4t. On the test, I'll give you this formula if you need it. You don't have to remember it. I've erased it, but the cosine of the sum, right? By equation 4 that we wrote up there is equal to twice the product of cosines, right? This is the one that's most popular in books, I think. Cosine plus cosine is 2 cosine cosine. And what you do is put in one of these, alpha, if you call this, I think I call that theta and gamma. I'll put theta plus gamma over 2, so I'll put 6t plus 4t over 2. And then I'll put theta minus gamma over 2, 6t minus 4t over 2, right? That's it. By equation 4, this sum is equal to this product. And now I just reduce a little. 2 cosine 10t over 2 is 5t. 2t over 2 is c. Now look, phenomenon of beats, right? I've got a cosine wave of angular frequency 5. It oscillates real fast, 5 radians per second. And this one of angular frequency 1 goes at 1 radian per second. And so you've got beats from the 2 cosine t that has, right, period 2 pi, since it's just cosine t, so it looks like this. Repeats after 2 pi, and then I get a 4 pi. This is this one, y equals cosine t. And then that's multiplied by cosine 5t. There goes five periods for every one this goes. And so it goes 2.5 periods between here and here. Anyway, it wiggles up and down real fast between plus and minus this way. So I'll draw minus this way. And it just does something like that. So phenomenon of beats comes out, right? A little bit. What happens is you really need to strike these at the same amplitude to get the full effect. If they're different amplitudes, then you get partly this effect and plus partly one of the tuning forks. But you can still hear it a little, kind of something clicking on and off. And you want them to be close in frequency, like 6 and 4 are kind of close to each other. It's not like 6,004, right? In order to get this, so that their difference is a lot different than their sum. That's what brings the phenomenon of beats out. But there's that one. So the homework problem, you don't have to draw the picture. The idea is to take this sum and rewrite it as this product, right? By the way, I should point out what your ear actually hears based on that last test that we had, the material for it, that is. Note, the other way of writing these, if you have a sine or a cosine, it doesn't matter. Sine of omega times t is also often written as sine or cosine of 2 pi ft. What is f? Remember? Where we just define f to be omega over 2 pi, so that omega equals 2 pi f. F is called the frequency. This is actually the number of cycles per second, or hertz, that you hear, or you see hertz on your electric box in your backyard, for instance, and so forth. This is the actual frequency and how many cycles it does per second that your ear picks up. This one is in radians per second because it's converted by this factor of 2 pi. So if you want to actually look at the notes on your piano or something and say, oh, it's this many hertz, this many cycles per second, that's f, and you write cosine 2 pi f, and this is your angular frequency, the radians per second. This is easier to write. This is what you actually hear is this frequency. So I'll just make that note that sometimes you'll see it written this way instead of this way, so you can pick off the actual number of cycles per second, pressure variation per second that your ear is picking up. So that's just a note on interpreting those things. And what happens is, since frequency is 1 over the wavelength, we recall from that, right? A high frequency has a long wavelength, that's this one, and a low frequency, low frequency has a large wavelength like that, and a high frequency has a short wavelength that goes up and down real fast. So they're reciprocals of each other, right? I was going to say, and I can't remember. All right. Let's leave that there. And we have one more problem here. Well, if we can do a sum to a product, we want to be able to do a product to a sum, right? So here's this one. Here's 1B. Right as a sum or difference. We'll call them sum to product identities, even if it's written as a difference, because a difference is just minus the cosine or sine of, minus the sine of minus the angle kind of thing. Okay, right as a sum or difference, suppose I gave you this one, 20 cosine 36t cosine 6t. How do I rewrite that one? Again, you don't need to memorize these, just look them up. I'll give them to you for the test. But you know that the product of cosines is 1/2 times the cosine of the sum of these angles, 36t, if you call this alpha and beta. All right. Cosine alpha, cosine beta is cosine alpha plus beta plus cosine alpha minus beta. And so we'll just rewrite it like that and say 36t plus 6t and 36t minus 6t. This is by equation 1. The very first one we derived for the product of the sum. And now let's see, this comes out to be 10. So these are each amplitude 10 waves, where you're summing a tuning fork or whatever, cosine 42t plus cosine 30t. So this is just going backwards. The product of these two with amplitude 20 is the sum of two each with amplitude 10. Okay, that'll do it then. Says we're about out of time, I guess. I don't think I have time for another example. So try those 3 problems on sum to product and product to sum. Fairly easy section. Despite my long write-up to show you the derivation, that's so you can figure it out if you need to and see where these come from. All the problems are just as simple as this. Thank you for coming in today.